Hi Chemistry 12-2 and welcome to week 6. We've made it! So we're going to continue our conversation with acids and bases this week. We're going to take a closer look at section 19.1 and the second half of 19.3, so in your textbook page 587. So there's going to be 3 videos this week. The first video will be on Arrhenius, acid and base definitions. It's going to be this video. Our second video is going to be on Bronston-Lowry, acid-base definitions. And our third video will be on acid-base, predicting acid-base reactions. There's a 5-step method that we'll take a look at and do some practicing with that. So just before we jumped in, I wanted to kind of make a list of what we know so far about acids and bases. You would have collected this information in grade 11 physics, sorry, not physics, in grade 11 chemistry you would have picked up on some of this information. We would have talked about acids and bases in 9-10 science, and we talked about acids and bases last week. So this is what we've got so far. We know that acids have a sour taste, and you might be like, what? People are drinking or eating acids? And of course, yes, it happens all the time. So we have a lot of acidic foods that we eat, and a great example of this is your sour gummy bears. They actually have a tartaric acid. They mix tartaric acid, which is an organic acid, and sugar together, and that makes the coating for the sour gummies. They turn blue litmus red. They have a pH less than 7. We found that out last week. They can neutralize bases, right? So if you have a basic spill, a spill of a very strong base, you can put a strong acid on it to neutralize that base. It also has some different types of reactions. So it reacts with active metals to produce hydrogen gas. We saw this in grade 11 when we took hydrochloric acid and we added some magnesium metal to it, and we saw it bubbling really quickly, and those bubbles were hydrogen gas. Reacts with carbonates to produce carbon dioxide. The famed science fair project, the volcano in elementary, where you take acetic acid, which is vinegar, and you take baking soda, which is hydrogen bicarbonate. So when you react those two things together and it starts to bubble up, it's the carbon dioxide that's bubbling up. And we know that they will react with OH compounds to form water and salt. And in this case, salt would mean an ionic compound. If you think about bases, they're caustic, another word for basic, and they taste bitter and feel slippery. I know this probably didn't happen to any of you guys. It definitely didn't happen to me. But as a young child, maybe saying some unsavory words and having your mouth washed out with soap, you might remember the bitter taste of that. Also, a lot of cleaning supplies are basic and they're kind of slippery to the touch. They turn red litmus blue, B for base, B for blue. They have a pH greater than 7, which we found. Strong bases are higher, up to 13 and 14. They neutralize acids. A base contains hydroxide, that's one of the indicators, and react with acids to form water and salt. Here we have Tums, which is a great antacid that you might use if your stomach acid is acting up, and it will neutralize your stomach acid. Here are some strong acids, and here's a key point. Aqueous solutions of acids and bases are electrolytes. There's that term again. And a reminder, electrolytes are solutions which conduct electricity. Okay, so both acids and bases, when dissolved in water, will conduct electricity. Now, before we jump again into something brand new, I wanted to kind of make sure we're okay with a few concepts, and I found some simulations and I thought they might help with our understanding. And the first one I wanted to take a look at is this one right here, and it's PHET simulations. And I just wanted to show you, it's a pH scale, so, and when we put in different solutions, for example, if I put in water, and this is just an easy simulation so we don't have to run into the lab, but you get the idea. And we know if we take that, because the H positives and the OH negatives are equal in concentration, we have a pH of 7. I thought this might be a good way of talking about the difference. Remember, right at the end of last week, we talked about strong acids versus weak acids, but also dilute versus concentrated. So strong and weak is all about the measure of H positives and OH negatives. But when you talk about concentrated and dilute, it means something a little different. It's about how much concentration, how much of that acid is mixed with the water, as opposed to just looking at H positives and OH negatives. So here we have water and it's neutral, and we can see that. Now if we empty this out, this is how this little simulation works, so let's get rid of that. What I wanted to show you is we have the option of putting different things in here and checking their pH. So just like being in the lab. So if we want to take some blood and we want to fill up our beaker with blood, we can put in that pH monitor and we can see just a little over 7.4 for blood. And we can empty that out. That must be a faster way. I guess not. And so we can take different things and look at it. And so you can see here we have hand soap. So we could put in some hand soap, and we could do this all day, which we won't, but you could check out different substances and just very quickly finding the pH. So that's a basic, right? Soap is basic, so that's a pH of 10. What I wanted to show you though is that when you look at pH, you know we're measuring how many hydrogen ions or how many OH ions we have. And we know if it's neutral, the H positive concentration and the OH concentration equals. But when we start to add water, what we're going to do to the soap is we're going to dilute it. So we know diluting means to decrease the concentration of your substance, of your solute. And if you take the water out, does it mean the same thing? Does it mean concentrating? Can you reconcentrate something after you've diluted it? Okay, so here we have this, and it's hand soap, and let's put in our pH measure, so it's 10. And when we start to add water, notice what happens to the pH. All right, as we're adding water to the solution, we're diluting it. And guess what? The pH is not staying exactly where it was. It's dropped a fair amount. It's still basic, but it's dropped a fair amount. So when we talk about pHs, we're talking about H positives and OH negatives. But when we talk about diluting or concentrated solutions, it means something a little different. So here we diluted it, which actually brought down the pH. Now here's the question. Can we remove that water now and go back to 11 and go back to the concentrated form? And the answer is no. Once we add water and dilute something, the only way we could, I guess, reconcentrate it would be to let it evaporate and then collect the crystals and add just the amount of water we had at the beginning. Okay, so I just thought that might help talking about dilute versus concentrated. The other one I wanted to take a look at is this one right up here. And this is neat because we've just finished talking about strong and weak acids, strong and weak bases. And we can see there's three things we can measure here. We can measure the pH, we can measure the litmus paper, so if we want to do a litmus test, and we can measure the, or a pH test, I should say. I don't know if it's litmus, I'm assuming it's litmus. And we can look at conductivity. So I just wanted to remind you of three tools we can use. So let's go back to our pH and let's take a look at water. And we know when we look at water, if you can see, here's the reaction that's going on. A billion of these and only 2 of them breaking up into ions, so heavily favoring. So you can see those ions of your H3O positives and your OH negatives. Now this is cool. We can put in, nope, that's not what I wanted to do. We can put in, maybe it's a different one I thought. Oh no, yes, here it is. We could put in all those water molecules that didn't break up if we wanted to as well. So that's why I think this is just a really neat simulation. So here's our acid. So let's just stick with pH. Go to a strong base. Hopefully that doesn't surprise you. Strong bases are completely ionizing, right? And so you can see that we have lots of the blue, which is our A negatives, and lots of the hydronium ions there. So high amounts of both. It's favoring the product. See, it doesn't have an equilibrium arrow. It's got that arrow there that has, it's quantitative, okay? And the pH is 2. Weak acid, we drop it. We've got lots of the H positive left over that didn't split. We're back to equilibrium, right? They only slightly ionize the weak acid. If we look at a strong base, pH is up here where we would assume it would be. And you can see we don't have a lot of these gray guys. We don't have a lot of this strong base. It's broken up into its M's and its OH's. They're using general formulas here. It has a quantitative arrow, so we can see how we have complete ionization or dissociation. And our weak base, again, lots of grays left over, so it's favoring the reactants. So it's got just slight dissociation, right? Weak dissociation. So we can see the difference, and you can see the difference here. So even a weak base is going to be up there, 9.50. And a strong base is even higher, okay? Whereas a weak acid closer to 7 and a strong acid closer to 1. Now there's different things we can test. So if we go back to our water, and let's now take a look at our pH scale, and you guys can predict what you think for the pH, right? Strong acid, where do you think it's going to be? It's going to be, why is that not going? Oh, maybe I have to physically put it in. There you go. You see the red color, which would make sense. Here you see an orange color, closer to 7. Here you see a blue, kind of a dark blue color for your strong base, up there with 12, 13, and 14. And a weak base, it's a lighter green down here at 9. So you can see this is not litmus, actually. This is called universal indicator, and you can see it has a different color for different pHs. And the third thing we can test, and I just wanted to do this before we jump into our next activity, conductivity, remember, electrolytes, solutions that conduct electricity. You need to have charged particles for electrons to be able to move through a solution. So if we head up here with water back again, what we do is we have to put both of these electrodes in, and if there's electrons here, if there's charged particles, it'll allow the electrons to travel through and close the circuit. So you can see water is slightly, right, see a little of the lights a little bit on, it's slightly conductive, and that's probably because there's a few ions in there. Strong acid, what do you predict? You are correct, a very strong electrolyte. Lots of charged particles there, so it's conducting electricity very well. Weak acid still conducts electricity, right? An acid has charged particles. Not as many charged particles, so it's not conducting as well, but it's still conducting electricity. Strong base, very strong again. Remember, quantitative reactions favoring the products, lots of charged particles. And a weak base, same as what you would predict. So those are just a couple simulations, maybe to help you out and to help you with this particular activity. So what I want you to do here, we're going to pause for a second. The problem here is which of the unknown solutions provided is HBr, CH3COOH, NaCl, C12H22O11, BaOH2, and KOH. So we've got these solutions, and what they've done is the solutions which have been prepared with equal concentration, which is smart, right? Remember, we want to have equal concentration so we can compare them specifically. They're each going to be tested with a conductivity apparatus, just like we saw, and with both red and blue litmus. So what they've done is they've taken 6 solutions rather, and here's the evidence table. They've done a test with red litmus, they've done a test with blue litmus, and they've done a conductivity test. And what they want us to do, what I want us to do, is we're going to take these 6 solutions and we're going to try and decide, just by looking at the data, where would you place each of these solutions, okay? So if you want to pause right now, if you've got some time, pause right now, take an educated guess, and then we'll come back and talk about them. Okay, so we're looking at this video, we've got some tests. How would we systematically go about this? Well, the first thing I think you should realize is that the first test they did is red litmus. And red litmus, when it turns blue, what's that tell you when a red litmus turns blue? And if you're saying blue for base, blue is correct. B for base, B for blue. So we have 2 blue. So that's telling me that solution 1 and solution 6 are basic. When we come over here, from your vast knowledge of grade 11 and last week, could you pick out which solutions here are basic? I hope you're saying the ones with hydroxide. So KOH and BaOH2 are our 2 basic solutions. Okay, so let's read on. no change and no change, which makes sense. So if the red litmus is having a change, the blue litmus is not. But let's continue reading. Conductivity. One of these bases is very high conductivity. The other base is just high conductivity. So of these two bases, which one would you predict has a higher conductivity? Which one would conduct electrons better? Which one would have more charged particles in the solution? If you're saying BaOH2, yes, because of this subscript 2. It means when every molecule of BaOH breaks up, it's going to release 2 of the OH ions, not just one of them. Now we have to be careful, and we'll talk about this a little later. Barium is a group 2. Barium has high solubility, so it's going to be a quantitative reaction, so it's going to break up very, very well. But there are some bases that have low solubility, so we have to be careful. But in this case, I would definitely put my barium hydroxide here, and I put my KOH down here. Okay, so you got to be systematic with these questions. Our next one here, you see there's no change, so I'm going to move on to the next test. With our blue litmus turned red, we know, or pink, that our solution 2 and our solution 4 is acidic. So when we come over here, can we find some acidic compounds? And from grade 11, hopefully you remember that acids start with an H or finish with a COOH or a koosh. I think that's what Mrs. Tate calls it, a koo maybe. But we have 2 acids here. So let's continue on. One of our acids has low conductivity and one of our acids have high conductivity. So when you move over here, we could do a few things. We know about Ka, so we could look up these acids and see which one is the stronger acid. The stronger acids, remember, they have 100% ionization, so they break up and create lots of charged particles, so they conduct really well. The weak acids, and this acidic acid is weak, it only has a low, slight ionization. So it will create charged particles, but it doesn't create a lot of charged particles. So this guy moves right in here where it has high conductivity. Oops, sorry, wrong place. Has low conductivity because it's not a strong acid, it's a weak acid. Weaker the acid, the weaker the conductivity. And here we apply that in there. So we got 2 left. And they're neither acid nor base. Okay, so they're neutral. That's our third category, acid, base, or neutral. So these guys are neutral solutions, but when we look closely, one of them conducts not at all, and the other one conducts quite well. So now you're really going to have to stretch it for grade 11. Which compounds conduct electricity well, which compounds don't? And we spend a lot of time on this. Ionic compounds start with a metal, and metals conduct electricity, if you think of anything, right? That's why you don't put a fork in the outlet. Metals conduct electricity. So this is an ionic compound. It's a metal. It's going to conduct electricity. This is made up of nonmetals. It's a molecular compound, and they do not conduct electricity. So we've reviewed a lot here. No conductivity for this. This is sugar. This is table sugar. No conductivity for this guy. And our salt is very conductive because it's ionic. So I just wanted to review a few of those things just to help you as we move forward. Red litmus to blue means base. Blue litmus to red means acid. Ionic compounds contain a metal and conduct electricity. Molecular compounds contain nonmetals and do not conduct electricity. All right, I think we're ready. So here's our next challenge. What I'd like you guys to do is to take a moment and to copy down these. You don't have to do the whole table, but just copy down these solutions here. So we have 3, 6, 9, 10, 11. There's 11 solutions here. Pause now and copy those solutions, please. Okay, so now that we've got these written down, what I want you to do is I want you to decide if it's an acid, a base, or if it's neutral. So we've done some reviewing. Use your knowledge from grade 11. Is it an acid? Is it a base? Is it neutral? Take a second to come up with that. All right, so now that you've paused and have come up with that, we're going to take a look at some tests here, okay? And the tests, I think we'll do it one at a time. So when we take a look at each of these solutions, our first solution is water. So you've predicted it as maybe neutral, I'm not sure. But when we look at our solutions here, right, no change, no change, that's a big hint. We're going to have a neutral solution, very slight conductivity, and it has a, right, it goes in as neutral. So the next one, HCl. Again, you found that H there, starting with an H. High conductivity, sounds good. Oh, look, it's red, makes sense. So if you predicted it was an acid, good to go. Our next one here, you probably haven't worked with a lot, but you probably went through your categories and you probably said, okay, so it doesn't start with an H, right? I don't know what you might have said it was an acid. You probably said it was neutral, but when we actually do the test, we see that we have high conductivity, which it's ionic, so that makes sense, but it actually turns blue. It turns red litmus blue. So it's actually put in the category of a base. That might be a surprise for you guys. Next one here, it's got an H, but it also has a sodium. So is it ionic? Is it an acid? Right? So you can start to see that some of our definitions might be in need of some repair or revision. So it has high conductivity, okay? But look at that. There's that blue. It turns it into a base, okay? Third one here, same idea. These guys all kind of look alike. They've got the sodium, they've got the hydrogen, but look how close they look. And they're ionic, so that doesn't surprise me that they have high conductivity. But this one actually turns litmus red. This fella right here acts like an acid. Okay? Moving on, here's our OH. You probably saw the OH right away and you knew it turned it blue, so we knew it was a base. Continuing on, here's another base. If you notice, this base has high conductivity, this base has low. It has to do with solubility. We'll talk about that in a second. And so we get our base, and we have our SO2 here. Right, this is sodium dioxide. It's not sulfate. It's sodium not even sulfite. It's sodium dioxide. And we see low conductivity, no charge. But look at that. How the heck is that an acid? But it does. If you do the test, it turns that litmus red. And so it's really, we really start to see some surprises here. MgO, okay, look, blue. There's no OH there. It's just MgO. But it's turning our litmus blue. It's classified as a base. Our last two, NH3, ammonia, right? Ammonia, you might say it's a molecule, right? So maybe it's neutral. It has low conductivity. Look at that, turns litmus blue. It's a base. And this one, hopefully, if you recognize it as acetic acid, see that COOH, you might have said it was an acid. Okay, so for the most part, I think looking at that and looking at our categories, most of you might have had maybe 10 out of the 11, 6 out of the 11 correct, if we were going with just the traditional definitions we have for acids and bases. So therefore, we are going to talk about some new, maybe some better explanatory definitions for acids and bases. Our first group, or first definition we're going to look at, it comes from a fellow named Arrhenius, or Arrhenius, I think is how you pronounce it. And Arrhenius acids and bases, we're going to take a quick look at his definitions today. So with Arrhenius, he basically said, kind of what we've been working on up until this point. He basically says, listen, does it start with an H? Does it contain an H? If it does, then it's probably going to be an acid. And if it contains an OH, it's probably going to be a base. So he looked for those two things like we've been trained to up to this point. If it starts with an H or ends with a COOH, it's an acid. If it has that OH, that hydroxide ion, it's a base. That's what we've been working with so far. We're going to have to fix these a little bit, but that's really what Arrhenius said. He said, acids are hydrogen-containing compounds that ionize to form hydrogen ions. So when they break up, they create H-positive ions. So that's got to be present. Bases are compounds that ionize to yield hydroxide ions, OH negatives, in aqueous solutions. Here's a little blurb on Arrhenius if you want to read about it. Monoprotic, diprotic, and triprotic. I've mentioned these terms before, but I'm going to remind you of what they mean. Protic means protons, so hydrogens. So any acid that has one hydrogen is called monoprotic. Any acid with two hydrogens is diprotic, and any acid with three hydrogens is triprotic. Okay? And we talked about that because even though these guys have multiple hydrogens, they'll lose one hydrogen at a time. All right, so you might say, does any compound that have an H act as an acid? That's not true, and Arrhenius knew that. So Arrhenius knew that not all compounds that contain hydrogen are acids. Okay, for example, CH4, methane. Methane has four hydrogens, but they do not turn red litmus, they do not turn blue litmus red, so they are not acids. Not all acids, not all hydrogens of an acid may be released. So let's take a closer look. This is key. Only hydrogens in very polar bonds are ionized, okay, when they are bonded to highly electronegative atoms. So if we look at HCl, and this is from grade 11, when we look at the electronegativity, it's a number that gauges how strongly an atom holds its electrons to itself. And so it ranges from 0 to 4, and chlorine has a very high electronegativity. What that means is even though the electrons are placed between the hydrogen and chlorine, they're closer to the chlorine. The chlorine has a stronger pull on those electrons. And so what happens is hydrogen says, all right, you can have those electrons. I'm going to split, and I've got that's where the hydronium ion comes from. So this is called a very polar, when there's an uneven sharing of the electrons, right? If they share evenly, it's a molecular bond. They're smack dab in the middle, right? So it's a sharing of electrons. But when the electrons are very, very closely tied to one element other than another, it's called a polar bond. So this is a very strong polar bond. And what Arrhenius knew is that if you have a very strong polar bond, the hydrogen in that bond is ionizing. So it's willing to leave because the electrons are closer to chlorine, so it's easier for that hydrogen to leave. And that's what we call an ionizing hydrogen. And so it breaks up quantitatively. And if you see the picture here, here's your water, here's HCl. This is a polar bond. So very, very easily that hydrogen moves over to water. And we have this negative anion and this positive hydronium ion. Okay? Now that's not true for everything. If you take a look at methane, we said earlier, when you take a look at methane and you look at these bonds here, if we checked the electronegativity, it's on your periodic table, between carbon and hydrogen, the electrons are actually quite evenly distributed. They're basically in the middle between these two. And so hydrogen is more invested in this molecule because this bond is not polar. It's a really weak polar bond. We can't say that it's covalent. Well, actually, we can say it's covalent because it is a covalent bond, but it's a weak polar bond because the electrons are more evenly shared between the two, and so hydrogen's more invested in this molecule. And so if we add methane to water, these hydrogens are going to stay put. They're not going to ionize. They're going to stay with it, and we're not going to have an acid that's being created. If you look over here, this is acetic acid, or ethanoic acid is another name for it. And you can see that we have both types of bonds here. We have carbon bonded to the hydrogen, and we have here very weak bonds. And over here, these guys are very polar bonds. This is actually they're smack dab right in the middle because carbon and carbon. It's a molecular bond. But over here you can see these are strong polar bonds. If you look at the electronegativity between oxygen and hydrogen, oxygen is a lot higher. So the electrons are closer to the oxygen. Hydrogen is not as invested. This hydrogen is not as invested in this molecule. And so this will ionize and this hydrogen can leave. So the hydrogens that end up leaving in acidic solutions are the hydrogens that are called ionizing hydrogens. And they're called ionizing hydrogens because they're part of a very strong polar bond, and it's easier for them to leave. These are not ionizing hydrogens. they are belonging to a very weak bond, and so they prefer to stay with the molecule. Why would we call this monoprotic when there's 4 hydrogens here? It's because only one of them is ionizing, so we call it monoprotic. You can also take a look at Arrhenius bases. So Arrhenius acids are compounds that have an H, or compounds that produce an H positive ion when put in water. A Arrhenius base is, just like we know, more concerned about hydroxide ion. So here we have sodium hydroxide and we have potassium hydroxide, and when they split apart into their Na and their OH negative, their K and their OH negative. Okay? And so, and this should not be a surprise to us. We've been working with this Arrhenius base definition for quite a while. Any compound that has OH, and when we put it in water, it ionizes so that we get this OH ion. Now we have to be careful here because not all bases that have OH are soluble, and that's going to change how much they affect the pH of a solution. So you can take a look at these. These are in your textbook. It says, based on your generalizations after looking at table 19.2, this table right down here, 19.2, is lithium hydroxide likely to be soluble in water? So there's a rule that goes along with solubility. We have a solubility chart, and so on the back of your periodic table, you can always check to see if your base is soluble or not. The general rule, group 1 bases are always soluble. They're very good. Group 2, not always soluble. Solubility increases as you move down the group. What I mean here is all of these guys, if they're connected with OH, they're going to be strong bases and they're going to ionize very well. But when you get into group 2, they're not necessarily all soluble. The solubility increases as you move down the table. So barium hydroxide is more soluble. Calcium hydroxide actually has low solubility. So you can check your chart, but that's the general rule as you move down. And so we've got to be careful because just to assume that all bases are soluble is incorrect, right? We have to check. So here, when you look at these two, your beryllium hydroxide, which is high in group 2, it's insoluble, but strontium, which is low in group 2, it's quite soluble. So this guy here would be better ionizing than this guy. This would be a stronger base than this guy here. Okay, so just be aware of that. And just a couple more things to share with you, just to kind of summarize here, and I'm just checking my time, because, oh, I'm all over very quickly. To summarize Arrhenius definitions, acids contain an ionizable H, that is substances that ionize an aqueous solution to form hydrogen ions. Bases contain an OH group, that is substances that dissociate to form hydrogen ions. You can take a look at these questions at your leisure. Here's 4. It's right out of your textbook. Let's bring it down here. And I just don't want to take too much time up for you guys. It says, how do Arrhenius definitions of acid and bases? So just reviewing the acid and base definition. And down here it says, identify the following as monoprotic, diprotic, or triprotic. So coming up with those definitions. Your answers are in your textbook, so you can take a look at these at your leisure. Here's a few more you could try. Again, thinking about those definitions. Here it says classify each of them using Arrhenius definitions. So are they acid or are they base? Do they have an ionizing H? Do they have an OH negative that they'll release in water? Write an equation for the dissociation of each of these compounds. So potassium hydroxide, what's that going to dissociate into? Magnesium hydroxide, what's that going to dissociate into? And you've got your definition, your answers here. Okay? And you, again, can see this should not be a surprise. You can check that out. And one last thing to finish with. There's one slight problem. But how can you explain why ammonia? Remember, if we go back to this table back here, we actually had several, find it here, of these guys that were surprises. Right? How the heck is this? Right? There's nothing there to tell me that this was going to be a base. There's nothing here to tell me that this is acting as an acid. So there are some weaknesses in Arrhenius definitions. And so That's why in the next video we'll take a look at Bronsted-Lowry definitions. But Arrhenius did recognize that there were some limitations to his definition, so he wanted to revise it. And so he did try to fix it. He didn't fix it so well, but he did try to fix it. And this is what he came up with, right? How can you explain why ammonia, there's no ionizing H there, there's no OH. How the heck is that acting like a base? Or vice versa, there's others that will act as acids. So this is how he revised it. He said, okay, and here's the equation here, ammonia, H2O, turns into ammonium and OH. So the water gives an H away, and it gets OH, right? So this guy didn't have his OH, but when he's in partnership with water, he can take one of those H's away, and he can still create OH negative ions. So Arrhenius kind of said, listen, you might not start out with the H, but if you can, in accompanying with water, if you can create an OH, then you can act as a base. So ammonia itself has none of the telltales that it's an acid or a base. But when we mix it with water, the fact that it will actually take one of those H's away from water and create OHs as a product, we now can classify it as a base. So here's his revised definitions. Basic solutions are formed when substances react with water to form hydroxide ions. So as long as they make hydroxide ions, they might not start out with hydroxide ions, but as long as they can make them when they ionize, they're going to be a base. Or same thing with acids. They might not start out with acids, with H's, but as long as they can produce hydronium or H's when they are finished, when they ionize, then he would classify them as an acid. Okay, so bases and acids. So just to finish off, and I know I'm running out of time, but I want to make sure you're okay to start your assignment. So this is my last thing. If sometimes we're asked to write out some equations, so I wanted to do a couple with you because I've asked you to do a couple on your assignment. Okay, let's test this explanatory power, the explanatory power of the revived Arrhenius definition. So let's try this. So write an equation showing how these anions react with water to produce a hydronium or a hydroxide ion. So how the heck is this going to create an acidic solution? Okay, now this is an anion. See, it has a charge there, negative. And so when you see that charge, you know you have a charged particle. If it's a negative charge, it's an anion, right? And so if it's an anion, I think I said it's up there. Sorry, I thought I hadn't put it up. This could be mixed. So this might be, this is known as the dihydrogen phosphate ion, right? Or, but I wanted to talk about spectator ions. So this might be, might have a sodium in front of it, like sodium hydrogen phosphate. Remember this chart again, the one we started with here. You have, see how you have sodium hydrogen carbonate, sodium hydrogen sulfate, sodium 2 carbonate, right? The carbonate, the CO3 is the anion. The HCO3 is the anion. The HSO4 is the anion. The sodium in front of it is known as a spectator ion. And so it's part of the molecule because ions don't exist on their own. So it's part of the molecule, but it quickly separates in water. And therefore, we really just need to look at the anion. We don't have to look at the whole molecule. So we're just looking at 2 anions here. And if we're going to solve the first one, I'm just looking for a cursor here. Okay, so we have H2PO4 negative, aqueous. Now we want to form, we're going to react that with water. And we want to form an acid. So what ion do we need for an acid? And if you're saying hydronium, you're absolutely right. So how the heck are we going to make hydronium out of this stuff? Now a reminder, sometimes I will write HOH here. It helps me a little bit for water. Technically it's a liquid. Okay, so what's going to happen here to get H3O? Well, we need to take one of the hydrogens away from the H2PO4. So what happens here, and I'm trying to get the cursor here. So what happens is, see this is H2O, or HOH, I'm going to take one of these H's, right? It's going to donate one of these H's. So that's where the H3 goes. But what's this guy going to look like after he's done? So what he's going to look like is HPO4 aqueous. And what's going to happen to his charge? His charge was -1, and I took a positive hydrogen away. So now he's going to have a charge of, I wish I had a cursor, -2. Okay, so H2PO3 aqueous plus H2O yields H3O positive plus HPO3 -2. So we want to be careful with our charges and with our aqueous. Let's try one more before you go. So we have PO4 -3, so it's an anion, right? So it's an ion. We're going to add it to water, which is liquid, and we want to make a basic solution. So what ion do we need for a basic solution? We need OH negative. So what the heck's going to happen here to get OH negative? Okay, and you guessed it, HOH, let's get rid of one of those H's. And that's what this compound's going to do for us. And so we can say plus HPO4. And what's the charge going to be? It was -3, but it's getting a positive now. So you're right, it's -2 aqueous. Okay, so when you gain H's, you get less negative. When you lose H's, you get more negative. Okay, so there's a few problems like that on your assignment. Thanks so much. I know I went late, but hopefully it was a good discussion on Arrhenius acid-base definitions.